You guys in the back of your homework spiral doing an exploration. That's quite a bit more intense than the one yesterday. Kyle just said, why can't we have A's and B's? And I said, well, isn't there something technically in the A spot and technically in the B spot? So couldn't you maybe start by pondering or considering A plus B to the 15th? And think of what would be there for A plus B to the 15th, and then maybe you can make a substitution for so if you don't like the 2x plus 1, that's okay. Think about it as an A plus B, and then after considering for an A plus B, go back and then say, okay, what if A is and what if B is? So it's not totally bad that your brain was like, ugh, I just want A's and B's. Cool, do it with A's and B's, and then think of what would change if I had a 2x for A and a 1 for B. The cool thing in math is there's this thing called substitution. We can use it when we need it. All right, pause. Everybody in the groups, I just want you to drop your pencils wherever you got. I want you to see if other people agree with you, disagree with you, if they even pondered or thought of anything. Talk it out. Pencils down, pencils down. Collaborate. How'd you get? How far did you get on this problem? Kim, it would have been really nice. You were working on this problem. Talk it out. Talk it out. Agree, disagree, have an opinion. If you don't have an opinion, ask help. I have no clue. Who has someone in their group that they're like, ooh, we think they're on the right track? Who has someone in their group that they're like, ooh, we think they're on the right track? What? Maybe. No. Wait, no one has any confidence in anyone in their group? Oh, Aiden. Or Kathleen. We had one hand point to Aiden, and we had 3 hands point to Kathleen. Kathleen, I want you to put your homework spiral under the webcam over there. Let's see what you got. Woo! Let's see. It's not punishment. It's a reward. That's okay. We want to ponder. Perfect. All right. Let's see what she did. You can grab a seat. It's okay. Kathleen, no, I mean here. That way I don't steal your homework spiral. All right, so she wrote down find the 5th term of 2x plus 1, all raised to the 15th power. Ooh, Kathleen, where'd you get this from? It's a good thing. Where'd you get it? Ah, she remembered it from doing homework last night. Does anybody else in their notes have anything that looks like what she just did?
I do.
I think I do too. Isn't it in this box? Doesn't it look kind of like this? Interesting. Muy interesante. So let's go back and see. So I see an NCR that she was using. Don't you guys? Now, why did she choose 15 and 4 for her N and her R? Kathleen, where'd the 15 come from? You can point to it on there. We'll see ya. Yeah, it's the 15th power. And then, wait a minute, why 4? I thought we were going to the 5th term. Adam, go ahead.
The A's descend, and so when you're at the 5th term, the X will be at the 11th power.
Did anybody else figure out that the A is going to be at the 11th power if it's the 5th term in? 15th, 14th, 13th, 12th, 11th. And if A is at the 11th power, what did we see yesterday? The two always add up to 15. So if one's 11, the other one is 4. What's another way of thinking about it? What does the B start off with? The first term, B is to what power? The 0th power. So wouldn't it be 0, 1, 2, 3, 4? So either way, you think about it, the 4 might make sense. So then if she knows n is 15 and r is 4 according to the formula, what was she able to do to finish off the term? Oh, ew, x and y. Kyle, isn't that even worse than a plus b? Oh, hey, what is x and y, though? Isn't it just a plus b? So technically, if you wanted to, couldn't we rewrite this formula to be NCR, a to the n minus r, and b to the r? And that might even be easier than x's and y's, because x's and y's, x is 2x, that's awkward. Y is 1. How about a is 2x and b is 1? So if we rewrote that little formula, does her solution make sense? Now, Kathleen, why are there lots of factorials? So she's using that formula? Good. So she was using her factorial formula, and what was she trying to not go to? Her calculator. So she was using the factorials, and then you see that she went ahead and reduced the 11 factorial. I agree. And then 12, 13, and 14. She could have gone 4, 3, 2, 1, and then crossed out a few more things. Whoa, whoa, whoa. But if 1365 is NCR, how on earth is her coefficient 2730? Oh, group, she was wrong. Or was she? Why is the number not the same? Split it up. What do you mean it's just the coefficient? But I thought the coefficient was 1365. That's the little guy that would be in Pascal's triangle and that spot. Oh, there's a 2x. Does that make a difference? So what's the one little baby correction that I'm going to tell Kathleen to make right now?
Put the x first.
No. X first. We always put coefficient first. Huh? 2x squared? No, she was right. It's 2x to the 11th. Oh, but is she right? This is correct, I think. It's way too small. Why is it way too small? Is Aiden right? Should 2 be to the 11th power? So the one correction I would make, parentheses around your 2x, because it's a to the 11th power, which means the entire a equals 2x to the 11th power, which means, Aiden, did you solve that way? Thanks, Kathleen. Grab a seat. Can anyone else, though? 2 to the 11th power times 1365? Kathleen needs to change it. So let's get a right number, because you guys need to change it, too. Before she sits down, let's have her change the 2730. It's not just double the 1365. It's 2 to the 11th times 1365. That's going to be huge. I don't know. You might need a lot of space.
Jeez. It's 2 million, baby. 2,795,000. You said it.
Whoo! Pause. Anybody have any questions for Kathleen? Any questions? Do we agree? Where'd the 1 go? What's anything times 1? Itself. Nice. Now, if there was something else in the 1 spot, wouldn't that have been a little different? So she just knew that 1 to the 4th was 1. So she could have written 1 to the 4th down there to make it look prettier. But it was right. 1 to the 4th is 1. So she simplified that. 2x to the 11th, well, that one needed a little bit of work. And then her coefficient came in. So question, once again, before we have her sit down. If she had done Pascal's triangle, what would have been in the row with the 15th power, 1 and then 15? Wait, did you guys notice that with Pascal's yesterday? Did you notice that? The second number in every single one of these was the same thing as the power. it was, well, 1, 0. That technically works. So then 1, 1, and then 1, 2, second power, 1, 3, third power, 1, 4, fourth power. So how would the row start off? That was to the 15th power. 115. And then if we had kept going over, question, what number could you have pulled out from Pascal's triangle in her work? This? 2,795,000? No. The 1365, because what lets us jump a place in Pascal's triangle? NCR. So that would have been Pascal's triangle, but would that have been the end of the story? No. You can't just put 1365 x to the 11th. It's 1365 2x to the 11th, a to the 11th times b to the 4th. Dun, 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 dun. Okay, last call. Any questions? All right, round of applause. Good job. Good job, good job. Your guys' applause stinks. Just wait until it's your turn. Anyway, so you guys like, I'm never doing one of those right again. No, no, no. Because who knows, maybe one time I'll be like, hey, point out someone in your group that made a mistake. Oh, no, a teacher wouldn't do that. Pause. How do we do everything in this class? Do I expect perfection? No. Do I celebrate mistakes? Not exactly, but do we use them to learn? Yes. So if there's ever anyone in your group that makes a certain mistake or that solves a certain answer, I might be like, hey, did anyone get? And you don't know if I'm saying it's right or wrong. So that's okay. Be proud. Be proud with your perfect work. Be proud with your mistaken work. Be proud with anything in between, because as long as you use it rightly, you'll still grow. Sound good? Okay. What do I mean by rightly? If you've done a word problem or even just any sort of problem, if you've done work perfectly, is there a wrong way to use perfect work? Is there a wrong way to use perfect work? I said use it rightly, so doesn't that indicate that there's a way to use it wrongly? Okay, so if you have perfect work all the time, just being like, here, let me just hand it out to people, and everyone just assumes you're always right, that's wrong, right? Because don't we all make mistakes? So you can't assume. We're going to start busting out in song, huh? So that might be a wrong way of using perfect work, but let's assume that you don't just pass off your work, or you don't have other people just assume that whatever you're saying is true. I try to stop you guys from that, right? Don't I say I make mistakes? Don't I try to have you guys check me and make sure that something that I'm giving you isn't just assumed to be true? Good pastors do that too. Pastors, like if you have a church, a home church, and your pastor gets up there, if he's like, you should always trust exactly what I say because I'm always right, please leave that church. Or at least start praying really hard for that pastor, because that's not going to be a good situation, right? What do the best pastors do? I'm human just like you. God is good, and let's try to learn about him together, right? The humble pastors are the best ones. Now, it doesn't mean they always have to divulge everything, right? I don't necessarily tell you every way I mess up. True? Okay. But even if your work is usually perfect, you still need to admit that you're fallible. You can make mistakes, right? So there is a wrong way to use right work. If you're like, psh, I'm always right, that's right, I am. That's not a right way. But is there also a wrong way to use imperfect work? We have to be careful that we don't get proud in our strengths, but what do we also have to be careful of in our weaknesses? Yeah. Yeah. So we have to be humble about our strengths, and we need to be gracious to ourselves and to others in weaknesses. Anyway, let's keep going, Life lessons, I don't know, all over the place in math, all the time. But what section are we in again, guys? Section 9.5, binomial theorem. Guess what? This example is kind of from the end of notes, so good job. Good job. Can I just show you? If you were to get down to the 15th row and actually start chugging stuff in, what it would look like. Oh, did you guys see yesterday? There's actually a shortcut way of writing NCR. What's the other way of writing NCR? Did you see it? Okay, N over R, but not with a fraction bar. No. Not with a fraction bar. Literally N over R, kind of like a matrix, but it's not. It's kind of like a 2 by 1, except in parentheses, not in brackets, so it's not a matrix. But that is another way of writing it. But if I was to show you this fifth term, another way of doing it could have been 15C0, 2x to the 15th, 1 to the 14th. That would have been the very first term. And guys, don't we know what the very first term is in Pascal's triangle? Isn't this going to always be a 1? Doesn't every row in Pascal's triangle start with a 1? The next one's going to be 15C1 with 2x to the what power? What happens to your A? He always counts down as B counts. Wait a minute, that's not right. I meant, okay, 1 to the 0, because don't these two need to add up to be 15? So I could have put the B if I wanted to. It would just be to the 0, which means poof, gone. But now all of a sudden he's appearing rightly, right? To the 1. What would your third term have been? Oh, wait a minute, hold on. In Pascal's triangle, even without getting there, we know the second number is going to be 15. But we could have plugged into the factorial-y thing and gotten them. Okay, what's going on here? 15C2, because now my 2x is to the 13th power. Do you guys realize that this A is always going to be to the subtraction of those two power? Because your B is that power, right? And then these two combine to be 15. So you can always just subtract n minus r. That's how that formula works. Do we know what that number is? Not without doing Pascal's. Or what? Or the factorial formula. So Kathleen did a great job of showing us her factorial formula about how she was plugging in. Some of you, without remembering what we had done yesterday, without getting very far in homework, you might have been like, don't worry, I got this. Just give me a little bit of time, because if I just have a little bit of time, and as long as I keep my mental math nice and honest, I mean, I'll eventually get there, because I'll just keep adding and adding and adding and adding and adding and adding and adding, right? And then I would get 35 and 35 and 21 and 7 and 1, and then I would get 1 and 8 and 28 and 56 and 70 and 56 and 28 and 8 and 1. Oh man, where do I have to get to, guys? 1 and 9 and 36 and 70, 84 and 126 and 120. Do you guys realize there's symmetry in Pascal's triangle? The coefficients count up, and at a certain point, either there's a middle or there's a shared, and then it starts counting down. That's kind of nice. It makes everything a little bit easier as you guys are going. And then we have 1, and then 10, and then 45, and then, oh, this is starting to get a little bit nasty, because now it's 120. Could we have kept going? But what's going to happen as we go from 1 to 11, and then 1 to 12, and then 1 to 13, and then 1 to... See, I'm going to totally run out of room, and if you guys notice, even when I did Pascal's triangle when I was younger and I was having fun, eventually my poor paper ran out, because not only is your row ever expanding, but also the numbers are getting bigger. And so all of a sudden you get into thousands and 10,000s and millions, and it squishes it all out, and it's just so sad. But what is the 1, 2, 3, 4, fifth number going to be? 1365. And it's so much easier just to use your factorial formula of 15C4 is 15. How does that factorial formula work again? N factorial all over n minus r factorial times r factorial. Man, it's nice to be able to jump, even though Pascal's is cool and all. Man, it's nice to jump. How could we double check if a random term is right in our Pascal's triangle if we ever had to check it? How can I check that that 126 really is what it's supposed to be without doing all the addition before? NCR. So who's my n? Can you guys tell just from this row? 9. It's the 9th power. And then what would my r be? What does this first one have r as? 0. Or you could think you start up at the 9th, 8th, 7th, 6th, 5th, 4th. 9 minus 4 is 5. Or you could count up the b term, 0, 1, 2, 3, 4, 5. So then you could go ahead and plug and chug that and be like, is 126 right? Well, it's going to be 9 factorial over 4 factorial, 5 factorial. Guys, how do we simplify? You saw Kathleen do it, but how do we simplify factorials again? Expand the numerator and see if anything can cancel. Or I would say expand the higher guy in general. Couldn't we make this 5 factorial, canceling out as much as possible, times 6, 7, 8, and 9? So that 5 factorial is going to reduce, but don't we still have 1 and 2 and 3 and 4? Well, it's not super exciting, except, oh, hey, 2 times 3 is 6. That's nice. And then, oh, 4 and 8, that can be 1 and 2. And then don't we just end up with 14 times 9? And 14 times 9 is just going to be 126?
Whoa!
Hey! So could we grab out my Pascal's triangle if I ever eventually find it? I know approximately where it is. And see if I was actually right in my bottom row as to where I stopped? Guess what? I totally went off. It was so sad. But anyway, she was still proud of how right I had been. But Pascal's triangle, it is one way to get to 1365. But can we glean from Kathleen's work and see that it's a lot easier just to use the NCR formula if you're jumping to a certain place? So anyway, we would keep going, and we would do 15C3, and we would have our 2x has now counted down. Oh, whatever. 15 minus 3 is 12. And then 1 is to the 3. And then we have our 15C4. Haha. 15 minus 4 is 11. 1 is to the 4th. Does this match up with what Kathleen got? Yes. Did you need to expand the entire row to find the 5th term? No. Did you even technically need to find the first 5 terms to get to the 5th term? No. The nice thing about binomial theorem is you can jump to a certain position in a binomial expansion. Binomial expansion? Oh yeah, because what are these? Binomials. And what are they being raised to? Powers. And condensed form would be the factored form. Expanded form would be the multiplied form. All right, cool kids, let's start playing with, oh, these problems then are easy, right? Oh, come on. So how would you do 8C2? In some context, I don't know, it's probably going to be applied in finding a term or finding a coefficient or, I don't know. But how do you just find it? Didn't we just talk about the formula? So what is NCR's formula? Those of you who are like, there's an NCR in my calculator. Great, don't use it. Don't use it. Not yet. You will be able to eventually in section 9.7. What? Where was it, Kyle? All right, let's let everyone know. Oh, okay, you could go alpha window or the math menu over to prob. What does prob stand for in the math menu? Probability? What? NCR is used in probability? Well, that's cool. Maybe it has multiple applications. Whoa, maybe binomial expansions are somehow used in probability too. They are. Pause, come back. All right, how do we do this by hand? N factorial over n minus r factorial times? Psh. Come on, you guys, you getting awesome at factorials yet? What should I rewrite 8 factorial to be? Because isn't it 1 through 6 and then a 7 and then an 8? And why did I stop at 6? Get rid of that guy. And then what's the 2 factorial? 1 and 2. Doesn't 2 and 8 become 1 and 4 and 7 is 28? Look at you guys getting awesome at factorials. Are we okay though? Remember, factorials count up from 1. So wait, what's going on with the 10 and the 3? Why are they on top of each other? Where's the fraction bar? Oh, that's right. What does this actually mean? NCR. Ready, set, you, yourself, and you. I want you to do 10C3 if you haven't yet. I want to know if you can do factorials by hand. Can you do factorials by hand? Oh, here we go. Just trying to find the post-it. Not for you, though. Don't worry. Naomi will do that. How was the test? Is it 120?
Yes.
Ooh, I can do factorials, NCRs, mental math in my head. What'd I just do to get 120? Maybe I should write it out first, right? What is it? 10 factorial over 7 factorial and? Okay. Who's the biggest factorial? 10. So break them down. 1 times 2 times 3 times 4 times 5 times 6 times 7. Ooh! Let's just write 7 factorial times.
8 and 9.
Are we tracking with why I'm breaking it down the way I'm breaking it down? 7 factorials. Zoop, there it is. Did I do 8 times 9 times 10 is 720 divided by 6? Ugh. No, because can't I reduce 2 and... Sure, to be 1 and 4, and can I reduce 3 and 9 to be 1 and 3, and 4 and 3 is 12, and 10 is 120? How you guys doing? Now, we have to know the formula first, right? So if you guys are highlighting kind of people, I see a couple of you already highlighted NCR, n factorial over n minus r factorial. Maybe also what Kathleen used in the beginning of class with that binomial term. That's a pretty important one as far as how to jump to a certain position in a binomial expansion. But then do you know how to go further by hand? What's special about these last two? One has a 0, which means this is technically what position in our whole binomial expansion? First. And what number is always in the first? So we could kind of cheat and be like, he's 1. Well, if that's the first position, 1 is 7 and the other one's 0, what's this one if 1 is 8? It's the last position, which means can't we also say, we start with the 1 pascals, you also... Okay, so we can cheat, but does the factorial formula work? 7 factorial all over 7 minus 0 factorial. Wait! Whoa. That doesn't work. Isn't that undefined? No, because what's 0 factorial defined to be? Oh, it does work. How about this one? It'd be 8 factorial all over 8 minus 8 factorial times. Oh, same thing, right? Because we'll get 1 over 0 factorial is defined to be 1. All right, NCR formulas. Wait a minute, have we already talked about Pascal's triangle? All right, so I want you guys to see how far you can go in 120 seconds starting in Pascal's triangle. Starting now, go. Expand. You might be like, but you said that wasn't very helpful to, for cubes and 4th powers, it's actually quite helpful to know Pascal's. You still have 1 minute and 45 seconds to go as far as you can in Pascal's triangle. We'll see the farthest you got, and we'll check your number and see if you're right. Some of your brains, sadly, kind of just memorized what I wrote, but hopefully you're doing it yourself, too. I'm going to start going off. Okay, stop freezing. Twenty seconds. 15. 10. 5, 4, 3, 2, 1. Pause. If you got at least to where I got, I couldn't tell my spacing, so I stopped. If you at least got to the 6th row, the 6th power row, raise your hand. Keep your hand up if you got to the 7th row. Or I should say 7th power. Keep it up if you got to the 8th power. Keep it up if you got to the 9th power. Keep it up if you got to the 10th power. Keep it up if you got to the 11th power. Keep it up if you got to the 12th power. Oh, we both stopped. All right. Adam and Wyatt, help me out. You were at the 11th power, right? Fill in the first few numbers. 1 and then 11 and then 55. Do you agree, Wyatt? Oh, the one before. Okay, keep going, Adam. 111, 55. 165. 330. 462. And then it started counting down. Okay, hold on. So let's check that 462. Kiddos, how can we check to make sure he was right? NCR. So what N do we have? We have 11 because he's in the 11th power row. And then R is going to be 1, 2, 3, 4, 5, 6. Wait, no. We start at 0, right? 0, 1, 2, 3, 4, 5. All right, let's check them. So we have 11 factorial all over 6 factorial times 5 factorial. 11 is going to be 6 factorial times 7, 8, 9, 10, 11, all over. And then we have 1, 2, 3, 4, 5. Can't 2 and 5 make 10? Can't, 3 and 4 makes 12. We're almost there. Okay, well, 3 goes into 9 3 times. 4 goes into 8 2 times. So we have 2 times 3 is 6. 6 and 7 is 42. And 42 times 11.
I'm guessing it's, oh no.
462. Dun, 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 dun. Bravo. Go, team. Okay, Pascal's triangle. We get the idea, right? Why is Pascal's triangle nice? Because, guys, if you have something basic like coefficients of 1 and 1, or even not coefficients of 1 and 1, but if you're squaring or cubing or fourth powering any polynomial, isn't it nice just to jump here and not have to do all that foiling and polynomial multiplication? You probably won't really be asked to go to the 5th or the 6th or the 7th necessarily, but Pascal's is super nice, especially for the first few powers of any binomial, to have that in the back of your mind. Go team, we already looked at all those patterns. So, how would you guys expand the following? It's an easier problem than we did in the back of our homework spirals today, except this one doesn't just want one term. What does it want? The whole shit. Oh, not 10. How many terms is a third power going to have? 0, 1, 2, 3. Does that make sense? 0, 1, 2, 3. Or you can think 4, 3, 2. No, sorry, 3, 2, 1, 0. There should be 4 terms. Ready, set, go. Is your brain going to 1, 3, 3, 1? Is your brain going to 1, 3, 3, 1? Makes life a little bit easier. You guys see the pattern? The A would be cubed and then squared and then first power and then gone. The B would be gone and then first power and then squared and then cubed. And then my coefficients are 1, 3, 3, 1. Who's my A? A equals X. Who's my B? But we wouldn't stop here, guys. We would write it in a pretty form, right? So what would our pretty form be? Well, that's just x cubed, true? Wouldn't that just be 3x squared times 1? And then 3x. That's a whole lot faster than foiling that puppy out. Questions? Is there a major pattern to the binomial theorem?
Yeah.
Big time. Is it going to be helpful to be able to work in that pattern and understand it and use it? Yep. Oh, this guy's nasty. But wait, you just did Pascal's triangle, and most of you got up to at least the 5th power row. Do you have the 5th power row?
1, 5, 10, 10, 5.
Got it. So we have 6 terms, right? Do we understand how I'm getting my first one? 1 is going to have A. Oh, nasty. They're using A's and B's. That's okay. Who's still in the first spot? 3A. So I'm going to use my 5. 3A is now going to be to the 4th. But question, kiddos, why when I bring in B am I going to bring in a negative 4B? because our normal pattern is a plus b to the n, right? Which I guess we shouldn't really use a plus b if they're using a's and b's, so fine, we'll use the book's x plus y. Either way. The binomial theorem is for addition, so we say, okay, fine, adding a negative. Don't you guys wish you had a smartboard? Although your lines are a bit longer than mine. Are my final numbers going to be 1, 5, 10, 10, 5, 1? Think Kathleen's example. Think all of your back of your homework spirals. I think it's going to be a bit more complicated. For instance, the first term is not 1, a to the 5th. The first term is 3 to the 5th, a to the 5th, or 243, a to the 5th. But was there still a 1 involved? Yeah. But there was also a 3 being raised to, and we had to include that. Does that make sense, guys? Now, why, though, right away, even though I'm used to writing plus, why am I going to come back and write a minus for the next term? The negative is being raised to the first power. It's going to come in front, and then I'm going to end up with 3 to the power of 4 times 20, because 5 and, oh, there's a 5 and a 4. So I'm going to end up with 1620, a to the 4th b. Why am I doing addition next, then?
Because the square.
Yeah, the negative's not going to make a difference, right? You guys getting 4320? A cubed b squared? But then I'm going to go minus again because now my negative's going to be raised to an odd power, true? I think I'm getting 5760.
Yeah.
How do you know when you're done? The a's should be gone and the b's should be fully raised to the power, which will be to the 5th. I'm going to do an addition next because I have an even power. 5 times 3 is 15. Times 4 to the power of 4. Is that 256? 3840? Oh, nasty. We don't even necessarily see like that pattern in Pascal's because all my numbers, I have the 1, 5, 10, 10, 5, 1, but we have all those other numbers as well. So the symmetry doesn't look quite so nice. And then finally, I have 4 to the power of 5. It's going to be a minus because I have an odd. And it's 1024 b to the 5th.
Huge numbers.
Huge numbers, but isn't it still easier than raising any binomial to the 5th power? Uh-huh. So then where are we going to end today? At jumping. At jumping. But am I going to expect you to write out the entire expansion of the 9th row? No. Why? Because all we need is the 8th term. Whoa, but it's n. Isn't that the power? Okay, it gets awkward. It gets awkward. In our formula, yes, this n is the power, but we're just going to say 8th term. There you go. So when they say the nth term, n is equal to 8, just be like, okay, fine, 8th term, and then n equals 9. It's okay, it's okay, it's okay. Don't stress. Robbie, hanging in there. Aiden, give him a pat in the back. You've passed on the sleepiness. So Kathleen isn't allowed to help us, but she's going to try it. The rest of us, Aiden, don't help us, but try it. Adam, don't help us, but try it. The 8th term, someone tell me something that we know about that term. Second to the last?
Yeah.
How is it second to the last? Tony, you said that. Second to the last, how do you know? It's the 9th power, and every time you have one extra term because of that 0. So there are 10 terms total. So it's a second from the last. So what do we know second from the last about the b term? Is that the easiest way to think about it? What's the last b term's power? 9. So 8. And if that one's 8, well then what must this guy be? 1. So then, what do I put in my C? 9, good, because it's the power. And then, who goes here? Is it the 1 or the 8? The 8. And then who's my A? And my B? And if it helps, guys, remember, didn't I say you should probably, that's awkward. Didn't I say something about you should probably highlight that general term of N, C, R, A to the N minus R, B to the R? If you wanted, you could have counted up and said, okay, starting at 0, because R always starts at 0. 0, 1, 2, 3, 4, 5, 6, 7. Ooh. Are we off? He said second to the last term. And Tony, in your brain it was right, but the English was a little off. Second to the last term, and then the one before. But technically, if there are 10 terms total and we're on the 8th, isn't it the second from the last? So it wasn't second to the last, it was the third one in. So what technically should be my R, guys? There are 2 terms after this. So the 9th term and the 8th term, this was the, I apologize, the B to the 9th, the B to the 8th, this was the third one from the end. So that would be the 7th. So Tony, I think you were in the right place, just the wording threw us off. So that should be 7 and 2, which means R is equal to 7. There we go. Guys, is this something that we can plug and chug and we can simplify and solve? You're already doing it? 9 factorial all over 2 factorial, 7 factorial of. Wouldn't that end up being 9 times 8? And that one's just 2 times 1, and that would be 4. Do you guys get 36 times 4 squared times 3 to the 7th, all times x squared y to the 7th? Sweet. Can we plug and chug that? Yeah, we can. 36 times 16 times 3 to the power of 7, not in the top of my head. Woo! 1,259,712 x squared y to the 7th. Someone back me up, please. Whoo! Go team. Man, this section is brutal. I wonder how much we have left. Oh! Oh, that's it. Okay.
What is that?
They're asking it in a different way. They're asking it in a different way. They want the term where, well, hold on. Can't we still say, okay, fine, we have x to something, we have negative 2y to something, and then we have n, which I know, c something. Does anybody see a way that we can figure out r? Because isn't that the piece that we're missing? Let's compare, wait, what they want to what we have when plugging in a and b and n. What do we know about r? Well, 8 is a little tricky, though. Can't I just match up?
Yeah.
So what does r equal? Plug it in, and we're done. Homework due tomorrow. Bye, cool kids. Binomial theorem, way to go. Play with those numbers tonight. Play with those binomials.